Hello again, ladies and gentlemen. Welcome to this year's last set of talks in the Geology lecture series at SWOCC. Man, what a long, strange trip it's been this year. It was just 51 weeks ago this morning. We had already had to cancel a couple talks, and we hosted a Mount St. Helens 40th anniversary doubleheader. Since then, everything has been virtual in the series this year, with talks on the gold rush in 1906, San Francisco earthquake, microbes in oceanic crusts like gabbro, whale seismology, radon, 3,000 years of sediment in You Are Who You Eat. And today our double header finale returns with seismology. So I'd again like to thank our sponsors who's been with us through many years, including this one, the College Foundation, Dallas and our IT department that do such a great job with the streaming, DB Western, the Mill, the Ocean Discovery Lecture Series, and certainly IRIS SSA, as both speakers today are part of the Incorporated Research Institutions for Seismology / Seismological Society of American Distinguished Lecturers Program. Our first speaker today is Dr. Guoqing Lin from the University of Miami. Dr. Lin earned her BS at Peking University and Ph.D. from Scripps Institution of Oceanography of the University of California at San Diego. She was also a postdoctoral researcher at the University of Wisconsin-Madison. Dr. Lin's talk will be followed today by Dr. Ben Holtzman of the Lamont Doherty Earth Observatory at Columbia University, and he'll be discussing seismology with your ears. I would like you to know that the chat is open for questions, and Dr. Lin will be available to answer questions following her talk, and she's planning to stick around after Dr. Holtzman's talk as well. Both of them have a little bit of information for us on Kilauea and the relationship between volcanism and seismology. So they're planning to be available to cover some of both of their talks after our second presentation, but we'll have a little Q&A after the first talk as well. First, it is my pleasure to introduce today our first speaker, Dr. Guoqing Lin, on the 2018 Kilauea Volcanic Eruption, expected or a surprise. Dr. Lin?
Hello, everyone. My name is Guoqing Lin. I'm a seismologist and a faculty member at the University of Miami. It's a great honor for me to be one of the 2021 IRIS SSA Distinguished Lecturers, and it's a real pleasure to be here with you all. Today, I will talk about a recent eruption at one of the most active volcanoes in the world, Kilauea Volcano in Hawaii. In 2018, Kilauea experienced its largest lower east reef zone eruption and the summit caldera collapse in at least 200 years. This eruption was one of the best monitored volcanic sequences in history and provides an outstanding opportunity for scientists to investigate volcanic phenomena. So I will use this eruption as an example to show you how seismologists investigate volcanic and seismic hazards. The outline of my talk is as follows. I will start with a brief introduction of Hawaii and the Kilauea volcano. Then I will show you some activities during the 2018 eruption. After that, I will present some preliminary results based on seismic data. And I will focus on changes in seismic parameters before and during the eruption, including seismic velocity, seismicity distribution, and focal solutions. Finally, I will summarize my presentation and talk about some future work. For seismologists, earthquakes are the main source of data to study the structure of the Earth and earthquake physics. This map shows the distribution of earthquakes above magnitude 5 in the past 10 years, downloaded from IRIS. The majority of these earthquakes occur along plate boundaries. In the Central Pacific, far from plate boundaries, sits a chain of islands with unique geological setting. That is Hawaii. The Hawaii Islands are volcanic, and they formed as a result of hotspot beneath the Pacific Plate. Hawaii Island, aka the Big Island, at the southeast end of this chain, is the biggest and youngest island. Hawaii Island consists of 5 volcanoes. The 2 in the south are the most active ones. Mauna Loa volcano is the largest shield volcano on the Earth. Its summit is about 4.2 kilometers high above sea level. In this picture, we're looking at Mauna Loa volcano from Kilauea. Kilauea, which is the subject of today's presentation, is the most active one. It's about 1.2 kilometers high above sea level. This shows Halemaumau crater in the summit. Now let's look at some major geological structures in Kilauea. This is the summit caldera. Here is Halemaumau crater. There are 2 major rift zones, the Southwest Rift Zone and the East Rift Zone. The East Rift Zone is often referred to as the Upper, Middle, and Lower East Rift Zone separately. The 2018 eruption occurred in the Lower East Rift Zone. There are also active fault systems marked by these blue lines. Here is the Kauai fault system, and this is the Helena fault system. In addition, the south flank of Kilauea moves seaward to the southeast direction at rates of up to 8 centimeters per year. This slide shows a 3D view of the recently updated model proposed for the geometry of magma storage and transport at Kilauea. It's mainly based on seismic, geodetic, and petrology data. There are a few major elements in this model. Here, in the summit magma system, it consists of 2 long-term reservoirs, one at about 3 kilometer depth beneath the South Caldera. Here is the map view. This is the South Caldera. And a slightly shallower one at about 1 or 2 kilometer depth beneath the caldera center. There's also the seismic Southwest Rift Zone and the volcanic Southwest Rift Zone. These are defined by the seismic and the magmatic activities, and they are connected to the summit reservoirs at different depth ranges. The East Rift Zone, with a molten core at about 3 kilometer depth, is connected to the South Caldera magma reservoir. Before the 2018 eruption, the East Rift Zone had been active continuously since 1983 near Pu'o crater. In order to answer the question on the title slide, whether the 2018 eruption was expected or a surprise, let's first look at the historical eruptions in Kilauea before the 2018 eruption. Eruptions in Kilauea mostly occur at summit and along its rift zones. In modern days, mainly in the summit area and the East Rift Zone. The summit area had many eruptions in the 1960s and 70s. There was a lava lake within Halemaumau crater, active since 2008. However, the dominant feature in Kilauea was the Pu'o eruption in the Middle East Rift Zone that started in 1983. This eruption continued for 35 years until 2018. For the Lower East Rift Zone, the most recent eruptions before 2018 occurred in 1955, 1960, and 1961. And based on this historical activity and the geological mapping, volcanologists actually have long known that the lower East Rift Zone was at high risk for lava inundation. However, the scale of the 2018 eruption was not expected. On April 30, 2018, the Pu'o vent collapsed and the magma propagated downrift. On May 3rd, eruptive fissures opened in the lower East Rift Zone. On the next day, May 4th, a magnitude 6.9 earthquake occurred. And in the meantime, the summit area experienced minor explosions and collapse events. And these collapse events are equivalent to magnitude 5 earthquakes. These activities declined in early August. When we talk about 2018 Kilauea eruption, we usually refer to two different types of activities. Here, the eruption in the lower East Rift Zone and the explosions and collapse events in the summit area. First, let's look at the timeline of the 2018 eruptive activity in the lower East Rift Zone. At about 5 o'clock in the afternoon local time on May 3rd, the first eruptive fissure opened within Leilani Estates. There were total 24 fissures, and most of them were short-lived, from minutes to hours. By the end of May, the eruption focused at Fissure 8. This shows Fissure 8 fountaining. Throughout June, Fissure 8 continued to supply channel, and lava entered Kipoho Bay in the eastern end. By early August, the major lower East Rift Zone effusion ended. This is the final lava flow map from the 2018 eruption. And this dark red color is for Fissure 8, which was active for over 2 months and formed the majority of the lava flow field. Next, I'm going to show you two videos for Fissure 8. The first one is recorded from the air. The second one from a web camera on the ground. All right. Next, let's look at what is going on in the summit area. In March and April 2018, lava levels at both the summit and Pu'o were observed to rise. In early May, small ash-rich explosive events started. By mid of May, the summit lava lake had drained. There were several small explosive events. In June, summit collapse events eventually involved larger portions of the caldera floor. In July, the collapse area became stable. By early August, summit collapse events ended, roughly coincident with the end of the lava effusion in the lower East Rift Zone. In order to display the changes due to these large collapse events at summit, I'm going to show you a time-lapse sequence of images recorded from a HVO camera. Here in the corner, you can see the time of each image. Approximately 1 image was selected per day. The collapse events started in late May. Started here. and the caldera floor dropped several meters during each of these collapse events. This is a final comparison before and after the eruption. And here in the central portion, the caldera floor dropped over 500 meters, and the volume change was over 0.8 cubic kilometer. This slide summarizes the activity in the lower East Rift Zone and the summit during the eruption. And in the meantime, the seismic activity also altered. This shows the number of earthquakes per hour in the lower East Rift Zone. The seismic rate abruptly increased in early May and during the entire month of May. And after that, the number of earthquakes dropped, but was still larger than before the eruption. In the summit area, although the seismic rate increased in May, the most dramatic change was the activity corresponding to the collapse events that started in late May and throughout June and July. So now let's look at seismic data. Hawaii Island has been serving as a natural laboratory for studying the interactions between seismic and magmatic processes for the past few decades. The Hawaii Volcano Observatory, HVO, has been operating an extensive seismic network to monitor and investigate hazards from active volcanoes and earthquakes in Hawaii. This map shows the HVO seismic stations, which are used in our studies. Digital seismic data are available from HVO since 1986. Before the 2018 eruption, there were over 370,000 earthquakes recorded by the HVO seismic stations. And you see the majority of these earthquakes occur in Kilauea Volcano, corresponding to the magmatic activity there. Here we show the number of earthquakes per day from 1986 to the end of 2018 for the entire Hawaii. This red thick curve illustrates the total number of earthquakes. And these spikes in the seismic rate correspond to the eruptive and intrusive activities over the years. However, the most abrupt change occurred in 2018. Now let's look at a close-up of the seismic rate in 2018. Again, here we show the number of earthquakes per day. And we see the seismic rate increased in early May and dropped in early August. And in this study, we refer to the earthquakes between April 11th and August 31st as the 2018 eruption sequence, because the seismic rate during this time period is greater than the background seismicity. Before we look at the earthquake distribution, let's look at something else. In recent years, a technique called ambient noise interferometry has been very popular among seismologists. Ambient noise is a seismic wave generated by either human or environmental activities, such as atmosphere and ocean waves. The basic idea of this is that we can use the ambient noise data recorded by a pair of stations or just a single station to calculate the changes in seismic velocity associated with changes in material properties of the subsurface. The advantage of this technique is that it doesn't rely on the occurrence of earthquakes. So we don't have to wait for earthquakes. As long as there are seismic stations, then we can apply this technique. Ambient noise interferometry has been a very useful and exciting monitoring tool at active volcanoes. And several studies have applied this method to the 2018 Kilauea eruption. Olivier et al. Used stations in the summit area, and they observed seismic velocity increase in March and April 2018, so about 2 months before the eruption. And they related this change with the gradual inflation of the edifice. They also observed a sudden decrease in velocity about 10 days before the eruption, and they attributed this to accumulating damage induced by the pressure from the magma reservoir. And additionally, there are these collapse events in the summit area. So here I plot earthquakes in June and July, and these are the magnitude. These red dots correspond to collapse events. And again, they are equivalent to magnitude 5 earthquakes. And Wu et al. Examined velocity variations corresponding to these collapse events. And this is a station in the summit area. And here, 0, that is the start of collapse event. And they show very clear velocity reduction before the collapse events, and also a gradual post-collapse velocity increase. And they associate this increase with reservoir pressurization. And after a few hours, this velocity gradually went back to the background level. So these results tell us that the subsurface velocity structure was changed corresponding to the major events, either the eruption or the collapse events. Okay, now let's look at earthquake distribution. In this map, I show distribution of over 100,000 earthquakes from 1986 to March 2009. So this is way before the 2018 eruption. These events are colored by the year of each earthquake. And you see that the seismicity is mainly focused in the summit area and the south flank. And next, let's look at the depth distribution along a profile AB in the summit area. So here we show the depth distribution along profile AB for all the earthquakes within this pink box. And here at the top, the pink dotted curve that illustrates the local ground surface. And the 0 depth here corresponds to mean sea level. It's about 1 kilometer below the ground surface in the summit area. And we see that the seismicity is distributed throughout the entire depth range, from the surface to 15 or even larger depths. Next, let's look at the depth distribution of these earthquakes along a profile CD in the south flank and the east rift zone. So again, here this is the depth, and this is the distance along profile CD from south flank to lower east rift zone. And again, this pink dotted curve, that is for the ground surface. And you see for this profile, the most obvious dominant feature is this, the linear structure at about 7 kilometer depth. That is the famous basal déclement in Kilauea, which is the interface between the volcanic edifice and the oceanic crust. And now let's look at the seismicity distribution during the 2018 eruption. This map shows the location of over 46,000 earthquakes. And these events are colored by the time relative to April 11th If you remember, we defined earthquakes between April 11th and August 31st as the 2018 eruption sequence. So here, in the lower East Rift Zone, these blue dots, they occurred in early days of the eruption, mostly in May. And in later days of the eruption, for these red dots, they mainly occur in the summit area and the south flank. And I also included some older events since July 2015, shown by these gray dots, mainly as a reference. All right, so now let's look at the depth distribution along two profiles. One along profile AB in the summit area, and another one along profile CD in the south flank and lower East Rift Zone. So these are the depth distributions during the 2018 eruption. And if we compare these with the background seismicity, so firstly, in the summit area, we see the earthquake distribution is actually quite similar between the 2018 eruption and the background seismicity. The earthquakes are distributed from the surface throughout the entire depth range, with a concentration at a shallower depth, about 3 kilometer depth. However, for profile CD, we see the seismicity distribution during the 2018 eruption is actually quite different from the background seismicity. Okay, now we put these two together for a better comparison. And the first thing we notice is over here in the lower East Rift Zone. And we see that during the 2018 eruption, the seismicity became shallower compared with the background seismicity. And this was due to the magmatic activity at shallow depths. And in addition to this, another difference we see is over here in the south flank near the Helena fault system. And we see compared with the basal déclement in the background seismicity, during the 2018 eruption, the seismicity was distributed into two subhorizontal bands. And if we look at the deeper layer, it's located at about 7 kilometer depth, and this is actually consistent with the basal déclement in the background seismicity. And the shallower one at about 3.5 kilometer depth, and this is a new feature. And because this is at a comparable depth with the seismicity in the lower East Rift Zone, so one appealing mechanism for this is that it might be related with magmatic activity. So this linear structure might represent dike intrusion. However, most seismicity in this new layer is actually located next to the Helena fault, and which is about 5 kilometers away from the East Rift Zone. So this is a little bit too far for a dike intrusion. However, this requires some further investigation. And an alternative interpretation for this new layer is it may represent the contact between the submarine flank of Mauna Loa volcano and the base of Kilauea volcano. And as a matter of fact, geological studies suggest that Kilauea is a relatively thin scab on the submarine flank of Mauna Loa volcano. And of course, in order to better understand this, we need support from other type of data. During the 2018 eruption, there were a great number of earthquakes. So now we would like to see what type of motions these earthquakes have and whether these motions changed before or during the eruption. So for a given fault plane, here. Based on the movement of the two blocks, faults are grouped into three categories: strike slip, normal, and reverse. So if the two blocks move horizontally, then we call it strike slip fault, which is usually caused by shearing forces. An example is the famous San Andreas fault in California. However, if the block above the fault moves downward relative to the block below the fault, then this is a normal fault, usually caused by tensional forces and results in extension. In contrast, if the block above the fault moves upward relative to the block below the fault, then this is a reverse fault, usually caused by compressional forces and results in shortening. The magnitude 6.9 earthquake on May 4th, 2018, following the eruption, is actually a reverse fault. And for normal and reverse faults, their motion is also called dip slip. And in reality, nearly all faults have some strike slip components and also dip slip components. So then we define oblique. And you may have noticed that these animations are from IRIS. So this is the website. And IRIS has the best outreaching material for seismology, and I use a lot of them in my class. I strongly encourage you to check them out. And so for strike slip and dip slip motions, in research, I often use something called scalar focal solutions. And of course, I will not show you how to derive these focal solutions, but instead, I use this color bar to identify the dominant fault type. So on the next few slides, if you see yellow or green colors, then that means it has a dominant strike slip movement. And if it's red, then it means it has dominant normal solution. If it's blue, it means it's dominated by reverse motion. So then I calculated the scalar focal solutions for all the earthquakes. And first, let's look at before the 2018 eruption. And here in the summit area, we see these solutions are green, so mainly strike slip solutions. And these solutions actually suggest stress concentration under the persistent seaward motion of the south flank. And the earthquakes in the south flank are mainly normal solutions. See, they are red. And these solutions are consistent with normal faulting of the Helena fault system. Next, let's look at the solutions during the 2018 eruption. So firstly, the summit area was replaced by a large number of normal events. And these normal solutions correspond to those collapse events. And in the south flank over here, we see these solutions became blue. Remember, before the eruption, they were red. They were normal solutions. And during the eruption, they are reverse solutions. And the majority of these earthquakes are aftershocks of the magnitude 6.9 earthquake. So the first thing that comes to mind is the change in the scalar focal solutions might have happened after this magnitude 6.9 earthquake. So next, we would like to see the time of these focal solutions within this pink box. Now here, we plot the focal solutions versus the time of their occurrence. So each circle represents one scalar focal solution. And again, we separate these focal solutions into normal, strike slip, and reverse groups. And the time starts with July 2015, and this is 2018, and this is May 2018 for the eruption. Then we calculated the average focal solution for every month. So here, each black square represents the mean scalar focal solution for all the solutions within that month and plotted in the middle of the corresponding month. And we see that before 2018, the focal solutions are dominated by normal solutions. And then during the eruption, there were a greater number of reverse solutions, and also for the eruption sequence. However, you must have noticed that the change in this focal solution actually occurred several months before the eruption. So here is January 2018. And we think this change actually started in December 2017. So in order to investigate what exactly caused this change in focal solution, then we plot the percentage of each fault type. So here, the red curve represents normal solution. And you see before 2018, that is dominant feature. And in December 2017, it dropped. And this green curve is for streak slip. And this actually didn't change very much during this time period. The blue one is for reverse solutions. And before 2018, there were not many reverse solutions. However, in November, especially December 2017, the number of reverse solutions greatly increased. And this tells us these focal solutions and their related stress field actually had changed several months before the eruption started. And this change in the dominant solution from normal to reverse is actually consistent with the magma pressurization in the East Rift Zone. Okay, here are just some take-home messages. In 2018, Kilauea experienced its largest lower East Rift Zone eruption and caldera collapse in at least 200 years. Seismology is one of the most important monitoring tools for active volcanoes. And because before and during an eruption or intrusion, magma and volcanic gas force their way through underground structures. And this may lead to a number of seismically detectable precursors. For the 2018 Kilauea eruption, studies have identified changes in characteristics of several seismic parameters. The most straightforward one is the number of earthquakes. So the seismicity rate was increased from about 30 events per day before the eruption to hundreds of earthquakes per day during the eruption. And the studies have shown that velocity also varied, corresponding to some major events, either the eruption in the lower East Rift Zone or the collapse events in the summit area. And also in the south flank, the dominant seismic concentration at that basal décollement was changed to that two-layer subhorizontal bands. And finally, we observed focal solution changes. And this change actually had occurred several months before the eruption started. And these results confirm that careful analysis of seismic parameters can provide new insights to the existing monitoring and can help seismic and volcanic hazard assessments and mitigation. The next several years offer an exciting opportunity to study the evolution of Kilauea following a major perturbation to its plumbing system. And there are many things on my to-do list. However, the first thing I would like to do is to conduct an experiment in the summit area of Kilauea by taking advantage of the recently developed and popular dense nodal array. And this is a picture of a compact 3-component node. It has a seismic sensor, data logger, GPS, and a power supply. So everything in this portable device. We can deploy 1,000 of them within just a few days. And these purple diamonds represent the proposed locations of nodes. And these nodes are very closely spaced, and it can help us resolve very fine scale structure in the subsurface of the summit magma system. And we submitted this to NSF last year, so hopefully it will be funded. And of course, seismology is one of the branches in geophysics. And in order to fully understand the complex plumbing system in Kilauea and Hawaii, we need to integrate geology, geochemistry, geophysics, and many other fields together. And I'm very grateful to USGS, HVO, and IRIS staff for making the data available for my work. And I thank my collaborators, Paul Okubo, Peter Scherer, and Falk Amelon. My work has been mainly supported by NSF, and here is a list of papers referred in my presentation. And thank you for your attention, and I look forward to your questions and discussions. Here is my email. Please feel free to reach out to me if you have any further questions afterwards. Thank you.
Well, thank you very much, Guoqing. I have had a couple of questions that actually are opposite sides of the same coin that are also something I'd say that comes up fairly frequently in my classes when we talk about both earthquakes as well as volcanology. And that's, sure, do earthquakes cause eruptions? And the flip of that, do eruptions cause earthquakes? And I guess we can throw in, can we expand your work on Kilauea elsewhere to other volcanic systems as well?
Okay, well, great questions, because I think these are the questions, many, not only seismologists, many scientists, are trying to answer. And the short answer is yes and yes. And actually, Kilauea is a very good example. And, for the 2018 eruption, because the eruption actually occurred on May 3rd, and the magnitude 6.9 earthquake happened the next day. So, a common idea was the eruption actually triggered the flank slip, so earthquake happened. And then, actually the idea is, this earthquake happened because it has, remember, it's a reverse fault. So it has this seaward motion and actually further facilitate the eruption in the lower East Rift Zone. And actually, before this 2018, this earthquake, the last largest earthquake happened in 1975. That's a magnitude 7.2 earthquake. And on that day, when that earthquake happened, the summit area erupted. And people believe this earthquake triggered that eruption. So, the short answer is yes. But of course, it doesn't mean every eruption will trigger earthquake or every earthquake will trigger eruption. It depends on, the style of eruption and, the type of earthquake. I mean, for Kilauea, both of these big earthquakes are reversed because they cause, seaward motion. So kind of, facilitated, helped the rupture in the summit and the East Rift Zone. Yeah. And also for expansion of my work to other volcanoes, And I have to say, Kilauea and Mauna Loa, these are the probably, two of the best monitored volcanoes in the whole world. And technically, of course, we can apply these techniques to other volcanoes. And I have projects, in other calderas and volcanoes, but it depends on, the station coverage. And if you ask, a seismologist, so what would you need, or, what would you suggest, to help the monitoring of a volcano? Our answer is always more stations. So it depends. So technically, yes, it doesn't, really depend on, the specifics of a volcano, but, we need data. But as I said, that ambient noise interferometry, that, technique, it doesn't really need occurrence of earthquake, but it still need stations. And the volcanoes, these are, kind of challenging to have permanent seismic stations. Some places just hard to access, and also, permitting, it's often a problem. So, I mean, again, theoretically, the answer is yes, we can apply all these to other volcanoes, but, depends on the data, the station coverage. Yeah.
So with all of the portable nodes, how concerned would you be with putting 1,000 of those out, as far as people just wandering in and bothering them, or trying to pick them up and take them away?
That's a good question. So this type of work, we need cooperation with the local people, and also, local agency like, HVO, so that they could help us monitoring. But, for this specific experiment, the plan, because for these nodes, they have their own battery, and usually they can last for months, and that's the the typical time period for this type of experiment. So if it's funded, then, all the people, PIs, this is, a collaboration with, a few USGS agencies. So, PIs, the students, and USGS, scientist staff, so we will be there, during, most of the experimental time. So, and of course, we will tell, the local people. And, Hawaiian people, they are aware of this kind of experiment. And during the 2018 eruption, there was a temporary nodal experiment, but that were only 50 of them, I believe. And for this kind of scale, it hasn't really happened, for, a volcano like Kilauea. Yeah.
Very good. This is a more general question, but I know that we frequently have students in the K-12 system, our community college students. What led you into science in general, and also more specifically into seismology?
Very good question. Well, I guess because I've been always interested in and good at, math and physics. And I feel, because geophysics, that's the application of physics to our Earth, right? And I always find it's intriguing. No offense to, mathematician or physician. And for me personally, because my home province is, has this volcano. It's called the Changbaishan volcano, and that's probably the most popular, well-known volcano in China. And so, since I was a kid, I was aware of, like a volcano, earthquakes, these kind of things. And you use something you learn to study, like, like everyday activity, just find it, fascinating. And I think, in order to do science, passion is one of the most important things. And I just love my job.
That's fantastic. Are there any suggestions you would have to any students that view this, as far as some of the things that they should do to prepare some of the coursework, some of the things that they might be able to do as extracurriculars to best prepare them for a STEM career or academic degree?
I mean, I think ARIS has this internship program, and I think it's actually probably for undergraduate students, and I think it takes place every summer, even during the pandemic. And for at UM, in my school, because we have geology, geophysics, atmospheric science, oceanography, and marine biology, then we have, many outreaching programs. So every summer we have those high school students come to our school, and then, students, they do a rotation, in different labs. And we also have something called Women in Science. So, those high school girls, they come, to our school, they work with, particular faculty. And for me, I always just, teach them how to turn their laptop into a seismometer. They usually just jump up and down, but they can see, the seismogram, And for your information, because now these outreaching components, the collaboration training of high school students, that's actually required by a lot of funding agencies such as NSF. So as far as I know, a lot of universities have these similar programs, and I think if somebody is interested, I would just totally encourage them to check them out, because we all realize how important it is to train our next generation as early as possible, right? So please study seismology. Yeah.
So we did hit something, and I'm going to lead with a question. This question is from Zhao Wei, and so I'm curious if Zhao Wei happened to have been a graduate student back in the day, some years ago at Iowa. You can type into the chat yes or no,
Okay.
and I know Dallas will find that. But I knew Zhao and Xin in Iowa. The likelihood is minimal, but I figured I would ask. So the question is, and I believe that you started to hit on this, she is wondering how long the nodal deployment will last, and will ambient noise be a problem, and also as tomography would be part of the study as well.
Oh, very good question.
How long for the nodal deployment, ambient
so for
noise?
how long? So the time period of experiment is usually limited by, the battery life of node. The advantage of these nodes is because they don't need solar panel, right? They don't need external power supply, and usually these batteries last for months. So that is why these nodal deployments usually last a month. And yes, ambient noise is a very important part of our proposal. And as a matter of fact, because we are very ambitious, we had seismic reflection and ambient noise and body wave studies. So pretty much everything you can think of in seismology. And ambient noise tomography, yes, because I'm the lead PI of this proposal, but we also have co-PIs and also USGS collaborators, and each of us has different tasks. And so I'm mainly just lead the body wave part, and my colleague, they will work on ambient noise tomography or reflection studies. So as I said, it's very ambitious proposal, and we don't know if it will be funded, but if it is, then it will be very, very exciting experiment. Yeah.
Fantastic. I think that's it on our questions at the moment. I appreciate your willingness to stick around during Ben's talk and potentially be available if folks come up with some questions while Dr. Holtzman is speaking as well. So thank you again for making time in
Absolutely.
your schedule. I know this has been an interesting
Thank you,
balance
Ron.
of time with East Coast, West Coast. So thank you,
Yes.
Guoqing, and we will possibly talk
Thank
to
you,
you
Ron.
again in a little while.
Okay.
Thank you.
Okay.
So, ladies and gentlemen, we are going to move on to our second speaker today. And again, I'll just kind of go with, I probably have some new folks. It was actually 51 weeks ago this morning that we hosted our first virtual geology lecture series talks. And just like today, it was also a doubleheader. That was a doubleheader celebrating Mount St. Helens' 40th anniversary of the last great 1980 eruption sequence. And we've had a number of virtual talks through the series this year. Fortunately, we've been live streaming these for a number of years now, and so have a well-developed archive of geology lectures. For instance, this season, we've had the gold rush in 1906, San Francisco earthquake, microbes in oceanic crust like gabbro, whale seismology, radon, 3,000 years of sediment in You Are What You Eat. And again, today our doubleheader returns to seismology. And so hopefully next fall we'll be able to return to the friendly confines of the Hale Center and be able to have a group of you face-to-face in the hall, as well as continue with the live stream for those that aren't able to make it live. I'd like to again thank our sponsors, the College Foundation, Dallas and our IT department, DB Western, the Mill, Ocean Discovery Lecture Series, and again, IRIS SSA, as both of our speakers today are part of the Incorporated Research Institutions for Seismology, Seismological Society of American Distinguished Lecture Series. Our second speaker today is Dr. Ben Holtzman from the Lamont Doherty Earth Observatory of Columbia University. He's the founder of the Seismic Sound Lab. He developed the Seismodome program at the Hayden Planetarium in New York City and is scientist in residence at the Computer Music Center at Columbia. He received his BS from Brown University and PhD from the University of Minnesota. As I mentioned, following the talk by Dr. Holtzman, both of our speakers will be available for questions following his talk. And I'm very pleased that Dr. Lin is willing to stay with us for the second Q&A session. Remember, the chat is open for questions. You're also welcome to email me questions if you have my email address, rmetzger@socc.edu. And that session will follow the talk. It's now my pleasure to introduce our second speaker today, Dr. Ben Holtzman, discussing seismology with your ears. Dr. Holtzman?
My name is Ben Holtzman, and I'm going to talk about doing seismology with your ears. And in particular, listening to patterns in tectonic, volcanic, and human-induced earthquakes. And before we start, I want to thank Ron Metzger and the organizers at Southwestern Oregon Community College and to Pearl Dorr at the Education Outreach Committee at IRIS for putting this talk together and making it possible. And also the National Science Foundation for funding this program through IRIS and the SSA. All right, now part of my work is to run the Seismic Sound Lab, and in this lab we develop methods for sonic and visual representation of data, ways of representing data using movies and sounds. And one of the questions we're motivated by is what we can learn about earthquakes by listening to the seismic data. And I want to thank the many collaborators and contributors who've worked with me on these projects and contributed movies that you'll see tonight. Okay. All right. So, what can we learn about earthquakes and how the Earth works by listening to and animating seismic data? I'm going to give this talk in three parts. The first one is tectonic earthquakes that are driven by mantle convection. and I'll show you what that means in a minute. And part 2 is volcanic earthquakes that are driven by magma trying to reach the surface. And part 3 are human-induced earthquakes driven by us, all by ourselves. So, first part, tectonic earthquakes. What is plate tectonics? What is an earthquake? And what patterns do tectonic earthquakes make in time and space? So here's a movie of 2 billion years in about a minute. And what you can see is the red is hot rock that is heating up as it's in contact with the core, and then it gets lighter and rises up to the surface where it starts to cool off and come back down as these blue blobs, blue and green blobs. So that's called convection, and these arrows are showing how the plates that are the rigid outer layer are moving around, being driven by those convection patterns. So on the time scale of 2 billion years, these motions look very smooth, but at the surface, most of them are accommodated by earthquakes. So earthquakes occur on the boundaries of the plates, here shown in gray. And those are the small, discrete motions that to us feel enormous. So what is an earthquake? Here's a good visual analogy for an earthquake and a little physical experiment that you can do right now. So take your fingers, lock them together like this, and push one arm away from you and try to hold that other one with the other one. Hold that arm back as long as you can until your fingers give way and it flicks. And as you build up, you're going to feel energy, tension build up in your tendons in the forearm. And that is elastic energy, and that's what drives earthquakes. And when your fingers snap, that energy is released, and that forms seismic waves. So what are we doing here? When we take seismic data, we're going to speed it up into our range of hearing. All right, so this is the range of seismic frequencies. So the frequency is how often something occurs per second. And the range of frequencies is much, much lower than what we can actually hear. So when you hear sounds associated with earthquakes, those are generally secondary sounds like the shaking of buildings, windows, pieces of concrete rubbing against each other, and that sort of thing. So we are going to take that data and speed it up. And here's an example. So this is a seismogram for this is about 4 hours, and we're going to play it back in a couple of seconds. And the little ant here is showing you the motion of the ground as in the transverse component. That's the top one of a seismogram. Right, so that bang was I'll shut up for a second. Okay, so that's a little bang that is from a very large earthquake, and we're going to play many of those, but that's just an example of what we're doing. Okay, so this is from the magnitude 6.6 earthquake in Niigata in 2007, sped up 4,000 times. And the ground motion is very exaggerated here, but here's the earthquake. This gray blob is where Tokyo is. And you can see that the energy lingers in Tokyo longer than anywhere else. And that's because it's a basin. It's a very weak rock. So it's kind of like a cube of jello being flicked, and it shakes much more than, say, the plate does right next to it. Here's the same earthquake, the same movie, 4 times faster. So this is going to be a little bit loud. And I do suggest wearing headphones because a lot of the stereo sounds convey motion of the seismic waves. But just to warn you, this one is a little bit of a crack. All right. So all of those, you hear the bang, and then all those little crackling sounds are aftershocks of that big piece of crust moving very suddenly and readjusting to its new position. Okay, so that's the local, a movie of a local wave field. But what happens to those seismic waves on a global scale? This is just an animation, no sound, of a simulation showing seismic wave propagation from a source right here and a seismometer right here, okay? So the waves are going to, they're P waves, the blue, and S waves here that are compressional and shear waves, and they're getting recorded by the seismometer as the ground moves, as those waves pass. And this group here is called the surface waves. And those body waves came and bounced off the core right here, and then back to the surface, right? So now we're going to take data from the magnitude 9 Tohoku Oki earthquake in 2011 that everybody probably knows about because it caused the huge tsunami that did a great deal of damage to the Fukushima reactor and nearby towns. All right, and with that, I want to issue a word of assurance that even though we associate earthquakes with tragedy, it is okay to find the following sounds and movies intriguing, scary, beautiful, whatever your reaction is to them, because they're just natural processes and the vast majority of them don't hurt anybody. And the tragedies occur because we do not build our cities and towns in the safest ways and in the safest places. And hopefully these kinds of movies will help people learn about where earthquakes occur. But just keep in mind that they're just natural processes, and we can react to them without associating them with what happens with their consequences. Okay, so here is a movie of the Tohoku earthquake. So the movie is a simulation, and the sounds are actual data taken from 8 seismometers around the planet. And the first 2 are filtered so that we hear the surface waves primarily, and the second 2 for the body waves. So here's the earthquake source. This is 2 hours of Earth time. Right, so you see the surface waves go on the other side of the planet and refocus and start to come back around to the source, and they'll keep doing that. After an earthquake this big, they'll do that for weeks and weeks. And these are the body waves. Okay, so now we're going to play another kind of movie that we call catalog movies. They're made from earthquake catalogs. And earthquake catalogs are just lists that we accumulate. As every earthquake happens, it gets analyzed and added to a catalog. So here's an example of one from the U.S. Geologic Survey called the ANSS Comprehensive Earthquake Catalog. And this is some, the data has time, latitude, longitude, depth, magnitude, and many other parameters. So we're going to take those lists and make movies out of them using, as an example, these are the kinds of rules that we use to generate the sounds and the animations. So the dot color is the dot size is magnitude. And the dot color is depth. And the sound is going to be filtered by the depth as well. So the higher frequencies don't make it to the surface. All right. So here's an earthquake catalog for 7 years of earthquakes in Japan, including the magnitude 9 Tohoku earthquake, and it will be very clear when that happens. So one thing you can see in there is that the earthquakes so the change in color from blue to red to orange to yellow is showing you that the depth is increasing as you go to the west, and that is telling you that plate, the Pacific plate here, is subducting beneath Japan. Now let's go to the other side of the Pacific, to Western North America, for 7 years. The first thing you can notice is that it's much quieter than Japan, so it's a much less seismically active plate boundary. Here's the San Andreas Fault. Here is Cascadia, where many of you are, right around here. And you can see this big gap in the earthquakes. I'll talk about that in a minute. Next, we're going to zoom in to California. Okay, so now we're going to hear the same 7 years with magnitude 6.6 and a little bit later a magnitude 6 in Parkfield, which is one of the most studied sections of fault in the world. And there are only 2 earthquakes in here, those 2 that were felt both in San Francisco up here and Los Angeles down here. So that's the sound. You could think of that as 2 plates sliding past each other, and they're always just just rubbing along and making lots of little earthquakes, and almost all of them aren't felt by anybody. But Californians are often talking about and worried about the big one that could be much larger than those two magnitude sixes. But I think, and I hope everybody in this audience and beyond knows about the potential for a much larger earthquake that would break the fault from basically Vancouver down to Mendocino. That is, has a recurrence time that's much longer than any earthquake in California. And so I want to play a movie that we made on data that is very subtle, that was discovered only about 10 to 15 years ago, called seismic tremor, that is happening on that subduction zone. So here's a sketch of the plate going down, and this area in here, kind of underneath the coast ranges in the Willamette Valley, is a source of episodic tremor and slip. So this tremor is coming here, and further out towards the ocean is what's called the locked zone, and that's where the earthquake would occur. All right, so here, this is a patterns of seismic tremor in the Cascadia subduction zone for 5 months in 2012. Okay. Okay, I recommend watching that again, but it really is a holy grail in seismology to understand if there is a relationship between the patterns in this kind of tremor and the beginning of a big earthquake. And that if we could understand that kind of relationship, if there is one or not, if there is one, it could give us even a little bit of warning for such an earthquake. So that is a very large open question in seismology. All right, so part 2, volcanic earthquakes. So the first, just a very brief overview of how volcanoes make sounds, the different ways, the different sources, and then something that we call the screams of redoubt, and then a really incredible data set for 48 days of earthquakes in Kilauea in 2018. So volcanoes are extremely complicated beasts. They have complicated plumbing, where you have deep magma chambers and all kinds of different pipes and tubes and sills and laccoliths and many other vocabulary words, and sources of magma and bodies of magma that are interacting and flowing up to the surface, and all of that movement causes some kind of vibration. So there are harmonic tremor and voices and things that sound like voices when we speed them up. There are faults and there are landslides and things that sound like drum beats. And so just to give you one example, we're going to play the screams of readout. And if you want to listen to more, you can go to this link, Volcano Listening Project, run by Leif Karlstrom. All right, here is, so readout is a volcano up in Alaska. And this is just one section of this seismogram. And right after that, there was a big eruption. So hopefully understanding these kinds of signals will help us be able to identify precursors to eruptions. All right, Hawaii. So Hawaii is a chain of volcanic islands in the Pacific, way out in the Pacific Ocean. And if we zoom in, you can see that chain. And if you could see into the mantle down to 1,000 kilometers, you would see a big plume of hot rock rising up from the core that's melting and causing the production of the volcanic islands. And if we zoom into the big island, and this corner, so Kilauea volcano is the youngest, most active volcano right over here. And in the summer of 2018, there was a very big eruption. A lot of lava flows. I'm going to kind of speed through this movie. But there were these lava flows on the on this rift near the coast. All right, so those were the lava flows in 2018, which were out here on this map. All right, but the crater of Kilauea is over here. Okay, and there was a big earthquake offshore over here right before the eruption started. So all of these things were connected to each other. And here's the movie. What happened there, I have never heard or seen anything like that before. Every day for about 48 days, there was a magnitude 5 or so earthquake, preceded by a bunch of small ones that built up. So we're going to zoom in to the crater and just listen to those 48 days or so. Not quite 48. So May 31st to August 8th. Here we go. so it just ended. When it stopped completely. So what is happening here? Somehow there is communication between what's happening out in the eruptions out on this rift and what's happening in the crater in the magma chamber below it. So what the relationship between the crater and the earthquakes and the lava flows that leads to this cyclic behavior is another really big and active question in volcanology and seismology. And there's a lot of research going on that right now. All right, so third part, human-induced earthquakes. How do we make an earthquake? And then I'm going to talk about earthquakes in Oklahoma and geothermal heat mining and earthquakes associated with that process, and then talk about these earthquakes in a context of questions about energy. So in 1969 to 1970, there was an experiment in making earthquakes in Rangeley, Colorado. And what people did was to inject fluid into these wells that went down about 2 kilometers into the crust, into the Weber sandstone, and all these black dots are earthquakes that resulted from pumping fluids down into the crust. So that was, I don't know if it was the first, but it was a very important experiment in demonstrating that we can make earthquakes. Now, what's been happening in the US since we began extracting shale gas, so when horizontal drilling was developed, and people realized that they could use it to extract gas from shale, so natural gas from shale, by causing small fractures in that rock, and then by pumping fluid in and then releasing the pressure at the surface on that fluid, and the rock collapses back down and pushes that fluid back up with all of its with this gas dissolved in it. All right. Now that has it had some benefits and some problems, but that's not what was actually causing the big earthquakes. The problem is that that fluid becomes toxic and has to be disposed of, and most states would not allow that fluid to be stored, and so it had to be shipped. And Oklahoma was one of the few states that it would allow it to be injected deep into the ground. So this is an injection well. It goes much deeper, and that fluid is being pumped at very high pressure. So it gets sent down into a deeper reservoir, usually formations that used to have oil in them, so they have lots of holes, and they can push that fluid deep into those rocks. But then when it intersects an old fault that hasn't moved for many, many years, it can reactivate that fault by pushing the sides of the fault apart and causing it to release any stress that's been built up on it. So these pink areas are areas that have shale that can produce gas and have been producing gas over the last 20 years or so. And Oklahoma has been the recipient of much of the wastewater fluids that come from these processes. So here's a history. This is from an article in Tulsa World showing injection. The injection started earlier than 2011, but the earthquakes kind of started in 2008, and by 2011 they were starting to ramp up. So the movie that we're going to show in a second is just the injection data here and the seismic, the earthquake catalog, right? And you're going to see this cap. So this is a kind of retrospectively defined cap in how much fluid could be injected. And all right, so the movie has a key like the other ones. The depth is 0 to 10 kilometers or so. And so you're going to hear the seismic sounds that are made the same way as the Kilauea movie, where we're clipping out the waveforms and speeding them up individually and then sticking them onto this timeline. So there's kind of two time scales of compression. So we're going to listen to 7 years in a minute. All right. If we just took 7 years of data, which would be an enormous amount, and sped it up, we wouldn't be able to hear anything. It would be above our range of hearing. So we have to do this in a kind of separate way. All right, and then the injection sounds are going to be these beeps with this slider showing how much fluid is being injected. Okay. Let me first say, so here's Oklahoma, and these gray areas are Native American reservations. So some of this activity, some of the wastewater injection and the earthquakes that result are happening on Native American land. Okay, so that was till 2018, and the number of earthquakes is still declining significantly. Okay, so now geothermal energy. This is a very different approach to extracting energy from the earth, where that has nothing to do with hydrocarbons, just trying to get heat out, and with that heat and the hot fluids, water, that turns into steam, and that can drive a turbine and generate electricity. So this is a map of what's called the heat flow. So how much heat is just moving through the crust and out into the atmosphere and into space. And you can see that the western US is very hot, and these blue areas are just sediments in basins that are kind of insulating, but underneath those sediments there's high heat flow. All right, and we're going to go to an area called the geysers, which is right up here in Northern California. All right, so geothermal heat mining happens by pouring or injecting or pumping cold water down into some part of the crust that is hot, and you need fractures, some kind of fracture network to connect the pipe, the fluids from the injection wells to what are called production wells, where the steam and hot fluids can rise up to the surface and hit a turbine generator and produce electricity. So here is a part of a movie from a paper we wrote on using machine learning to characterize these earthquakes. But this is just the earthquake catalog itself for 3 years. these are much smaller earthquakes in a much smaller area than in the ones I just showed you right behind. So this is the geysers geothermal field in California. And they're pouring cold water into this reservoir, and that's causing small earthquakes. And then heat is coming out through the production wells in the form of steam and driving turbines. Okay, so how do we consider hazard from human-induced earthquakes in the context of climate change? So this is a kind of diagram that I find very interesting that are produced by the Department of Energy, in particular Lawrence Livermore National Lab in California, that show the flow of energy through our society. So on the left are all the sources of energy, and on the right, on the far right, are showing how much is actually used to do work or heat or run automobiles, and how much is lost to heat, right? And so you can see that geothermal right now is a very small, these are in units of what are called quads, which are 10 to the 18 joules, right? So this is an enormous amount of energy. So geothermal right now is a very small fraction of our total use. Most of it goes to electricity generation, and some of it goes into residential and commercial heating. All right. Natural gas is the second largest source of energy right now, and it's going into electricity, residential heating, commercial, and industrial processes, and a small amount into transportation. All right. So here's a kind of a comparison of the benefits and risks of these two sources of energy and earthquakes. All right. So the first point I want to make is that it is better globally, right, to produce the energy that we use as a society locally, right? There's less energy wasted in transport, and also we see and feel and have to confront the environmental consequences of that energy source. So the contamination, all the problems of earthquakes caused by disposal of fluids are environmental consequences that we're dealing with because we're energy independent, which is a good thing. Okay, but people tend to focus on those earthquakes as the negative consequence of fracking, and this can be misleading. So the earthquakes have caused lots of damage to buildings and roads and infrastructure. As far as I know, nobody has been killed by the earthquakes. There was one injury in the 2016 5.8 Pawnee earthquake, which is the largest one. But the real hazard from the earthquakes and directly from the pumping of the wastewater injection may be the contamination of groundwater. But that's a much more abstract and uncertain and unpredictable kind of hazard. And so people tend to focus on the more concrete ones that are the earthquakes. And the main problem, of course, is the role of CO2 that is, causing climate change. And but climate change is also a relatively abstract and hard to predict consequence, right, of CO2 production. So it's getting more and more concrete, but compared to earthquakes and the very clear causal relationship between groundwater pumping into underground reservoirs and the production of earthquakes, climate change is more abstract. All right, geothermal heat mining. The seismicity is on a far, far smaller scale than from wastewater injection in the U.S. So that was that area in the geysers, which has the highest seismicity rate of any geothermal reservoir, is producing CO2 free electricity and a very, very small number of earthquakes. And the fluid that's used for that heat mining has no added chemicals, so there's a much smaller risk of drinking water contamination and other kinds of contamination of aquifers. And geothermal is an inexhaustible supply of CO2 free energy. So just to end this, I just want to end with this thought that when comparing these energy sources, it is easy to focus on the earthquakes because they're concrete and frightening, but that misses the real hazards and the benefits of these two energy sources. So I am happy to take questions after this talk, and if you're listening to the recording, feel free to email me. And all of these movies are on our website. My name is Ben Holtzman, and I'm going to talk about
you again, Ben. Very much appreciate both Dr. Holtzman and Dr. Lin making time in their schedule. It's been an interesting balance on making this work, East Coast, West Coast. So used to, over the years, having things in the hall and everybody staying here. One of the things that I'll point out, actually, just a couple things. One, who'd have thought that whale seismology and volcano seismology, as far as sonically, sounds essentially the same, and how we end up getting that information and putting it into different speeds to magnify those things is always cool. And I appreciate that episodic tremor and slip when that was a relatively new thing. And I was late to the game in doing the live stream and the archiving. I've always believed in live events being live. But I was going to have Herb Draggart come down, and it was also probably in one of those days where Herb had something come up where he couldn't come down. He probably handed the plane ticket to Kellen Wang, who came down and gave the ETS talk down here. And a few years back for the Cascadia anniversary talk, we had one that was focused on human-induced earthquakes with Justin Rubenstein. So it's just, I always love that interconnectivity and correlation between what's going on now and what we've hosted over the last more than 15, pushing 20 years now here. So I've gotten a couple of emails in. And so one of them, I will admit, I thought of this, but I'm guessing that both Dallas and I were thinking that the sonic 7-year cycles of earthquakes would have sounded amazing in the Hale Center with the audio system in there. But what the question had, and that was in the back of my mind too, have you ever had PTSD or similar issues at any of your talks that are, people don't have that personal control on? Oh, and it looks like we have, I don't know if you can hear me, Ben, it looks like we have some connectivity issue as well. So as we all get tired of Zoom, can you hear me? Okay, because we can't
Try
hear
again.
you. No. And when it comes to technology, I know this is out of my field.
Still,
Can you hear
can't hear
me,
me at
Ron?
all?
Okay,
Good.
try again. Ben?
Can you hear me? Yeah. Can
Yep.
you hear me now? Okay.
Yes, we can.
Great. Good. So yeah, I don't think I can't think of any PTSD kind of episodes that people have experienced. We do, we always warn people what the sounds might be like, and I think that helps. Yeah.
No, that's actually a good thing
But I have worried
that it
about it.
hasn't. Another one that came in was, what is Seismodome, and is it only in New York City? So do I have to go to NYC
it was
to participate?
Well, it was a show, so it was only, we did it 5 times, but using a lot of these movies. But the thing about it was that you're inside. We used the planetarium in a different way than it's usually used, where the spherical dome screen was actually the surface of the planet, and the audience was inside the planet. And so you would see those movies of seismic waves moving around the surface where you're inside the planet. And the sound was moving. They had a 24 speaker system. And so the sound, the motion of the sound was a very big part of the show. So unfortunately, we can't do that, but I will actually be visiting the University of Oregon this fall, and they have a small planetarium, and we're hoping to be able to play with some earthquake sounds in that. So if that becomes a show, I'll let you know.
Sounds good. Another one that came in, can you feel the surface waves on the other side of the planet or on their return path?
Yeah, so it's a great question. So the surface waves are very low frequency. So they're like, they can have a kind of up and down time of about 100 seconds or so. And so the displacements can be large. It can, like when the Tohoku earthquake happened, New York went up and down a couple of centimeters, but it happened so slowly that we can't feel it. Right. So because force is mass times acceleration, and the acceleration is too slow for us to feel it.
I'll ask you the same questions that I asked Dr. Lin earlier. What initially got you interested in science and seismology, and also any suggestions you might have for students interested in STEM degrees or STEM careers?
Oh yeah, I mean, well, let's see. I was interested in both when I was in high school and college. I liked science. I liked being outside. I liked geology, biology and stuff. But I also was interested in filmmaking and visual arts and things. And I ended up studying geology as an undergrad. It was a no-brainer. I just went straight for it. But then I moved into rock physics, and then eventually, when I moved to Columbia after grad school, started to get interested in seismology. So I'm a very late comer to seismology, and probably wouldn't even call myself a seismologist, but more just general geophysics. And advice is just if you have the ability and freedom to study what interests you, go for it, and try to find opportunities to work in labs and get your hands dirty figuratively speaking, but the science is really about the unknown, and you got to love not understanding things as much as you are interested in the processes themselves. So, yeah, curiosity.
So I know Guoqing started with Kilauea and connections with seismicity at the beginning. And Ben talked to us, amongst many things, about Kilauea and a couple of other volcanic issues. Do you have anything you would like to bounce off one another? Since Dr. Lin was kind enough to stick around, I haven't gotten anything in the email box or that I've seen come up in the chat box. So basically, we've never had the opportunity to have the speaker question, speaker concept. So, and something still may come in as well.
Yeah.
Well, it's a fantastic presentation, Ben. I mean, especially because I talked about those, summit collapse events, but it's just, oh my gosh, in Ben's movies, then you see all those, events for, 48 days, 62, big collapse events. It's just, fascinating. Yeah. I don't know if we'll have time, I just have this general question for Ben. So you showed, different types of earthquakes. So, you're an expert on this. And by listening to these earthquakes, can you tell the difference, say, between tectonic and induced earthquakes? Or, is there anything specific for each type of these earthquakes?
Yeah, that's something that we are always thinking about and working on. And I think one thing I can say right now is there's a huge amount of variability in the sources themselves, right? The sounds of the actual rupture and the frictional behavior of two rocks rubbing against each other, even within one setting. So you could hear a lot of different sounds in the volcanic setting and in Oklahoma, but what's very different are the temporal patterns and the aftershock sequences. And so the San Andreas, the characteristic thing, and the same with the geysers, earthquakes, is that there's just always the stress is always there. So there's always some degree of buildup and release, and then punctuated by larger events that have a kind of characteristic decay. But Oklahoma is just totally different, right? It's like there's no, the kind of background stress driving earthquakes is not there. So it entirely depends on that forcing of the fluid injection. And so the temporal patterns are very, very different. The kind of probably the aftershock patterns as well in those settings. And Kilauea, volcanic earthquakes they're just very, very different from one volcano to the next. And I've never heard anything like that Kilauea sequence. I learned a lot from your talk too. I really liked.
Thank you.
So I hadn't realized that there was an eruption right before the magnitude 6, the offshore one, and so the interaction of to what extent that helped trigger the offshore earthquake. It seems to be a really interesting question, like someone asked afterwards. But I did want to ask you a question. In the movie, especially the second one, where you hear the low frequency, you hear the buildup every day, and those are kind of high pitched crackling kind of sounds. And then the magnitude 5 is always a thud, right? It has a low frequency.
It's a very low
frequency. The high
frequency,
frequencies are gone. They're not they're not there. Yeah. I'm wondering what you're
It's very
thinking
interesting.
about why that is.
Oh, why? Well, I think presumably because
Yeah.
during that time, because the magma in the summit area kind of transported to the middle and the lower East Rift Zone, and I mean we can think of this as like piston, right? So you feel because there's a like mass removal because you lost some mass, then it can't hold the surface anymore. Then it just collapsed. Then it reached some kind of a balance. But after, as you said, after like 24 hours, those foreshocks, it's, the pressure, just kept building up and the magma, kept just migrating to the middle or lower East Rift Zone. Then at one point, again, it can't hold it anymore. So 24, 28 hours later, another big collapse event. So that's my interpretation. It's, how this, the summit area and the middle lower East Rift Zone, they connect with each other. But I mean, as you said, because it's never happened, at least, in modern days. The lower East Rift Zone eruption, had triggered some kind of summit caldera collapse before, but not in this kind of scale. And also, as you mentioned, people believe that magnitude 6.9 earthquake, that probably, kind of helped this whole rupture, this sequence, this whole thing. So, but I mean, it's very complicated and very interesting. Yeah.
Yeah. I guess I've wondered if there was if the rupture for the fives actually it hits the magma, so it doesn't complete its displacement and kind of gets caught by the magma. Is that even possible? And that would absorb
possible,
some of the high frequency energy.
I think it's possible because I mean there is some high frequency content in the the signal, the seismic signal, but it's hard to know. I think a lot of us will spend quite some time studying this whole sequence, but I think it's possible. There are different hypotheses. Yeah.
And I guess that's the beauty of science. Every time you answer half a question, you generate 3 or 4 more. I'd like to again take a minute to thank both Guoqing and Ben for participating in this. I know one of the things that I really enjoy is being able to host speakers to show off our backyard, which is pretty spectacular in many of its own ways. And I also appreciate their willingness to participate in this event at a point in time when I know most of us are pretty tired of Zoom meetings and virtual components. But I truly appreciate, because I've been indebted to the speakers that have been willing to travel near and far for years to participate in this lecture series. Without them, it wouldn't be successful. Without the audience that will either show up in the Hale Center or show up virtually, we wouldn't need to do it if they didn't participate as well. And same thing for our sponsors. So I'd like to thank both of you. I'd like to thank again IRIS SSA and everybody else that's contributed to having a successful virtual lecture series this year. We may have to do a little bit of this at the start next year. Hopefully, fingers crossed, we'll be able to just kick off right in the Hale Center. But one thing that we do know is we'll continue to present cutting edge science in SWOCC and throughout now the airways. So thank you both very much for your participation, and thank you all for listening. Everybody stay safe, take care.
Ron.
We'll talk to you soon.
Thank you too.
Thank you.
Thanks, Ron. Thank you, everybody.